So, good morning, everyone. I think it's their afternoon. So, I'd like to introduce myself. So, me, Kamrul Islam, and I would like to present my appraisal study of similarity-based and embedding-based approach for link prediction on graph. So, here's the list of my agenda for the presentation. First, I would like to introduce the graph. Everybody knows that. And then I will talk about the link prediction problem and approaches to solve the problem. And then I will discuss about two popular approaches for link prediction, similarity-based and embedding-based approaches. And then I will go to my experimental results section. Then I will conclude with my contributions and conclusions. So first of all, what is graph? So in simple out, graph is a structure that consists of some nodes that represent real-world objects and links between those objects. And here you can see this is a simple graph that contains some nodes, A, B, C, X, like that. And the links, the line represents the links. So there are several types of graphs, like homogeneous graphs. In homogeneous graphs, all nodes are of same types, and graphs may be heterogeneous, where a graph where nodes are from different types. And graph may be undirected, directed, or mixed. So if the link have direction like from A to X, but not from X to A, so this is called directed graphs. But if the link have no direction, so it is called undirected graph. And in mixed graph, some of the links have direction and some of the links don't have direction. And also graph may be a weighted graph where each links have some numerical values, and graph may be unweighted where the links actually don't have any weight, any values. So here is the example of some of the real-world graphs. So Amazon co-purchasing, where if two persons purchase the same product, so they are connected. And protein-protein interaction graph, DVLP. This is an academic collaboration graph, and also drug-drug interaction graph. So what is the link prediction problem? So link prediction problem is the task of predicting actually the probability of a link between two unconnected nodes in a graph. So in the link prediction task, so actually link prediction tasks use the available graph information like node attributes, structural information, etc. And here is an example of a link prediction problem. So in the left graph, you see there is no connection. There is no link between X, node X, and node X or Y. And link prediction method actually discovered the link between X and Y. So this is the task of link prediction method, to discover the link between unconnected nodes. And some of the application of link prediction include friend recommendation in social network, product recommendation in e-commerce network, drug repurposing in drug target network, and also for knowledge graph compilation. So what are the available methods in the literature for link prediction problem? So there are 4 broad categories of link prediction methods. So first of all, similarity-based method, then embedding-based method. So factorization-based method, probability and statistics-based method. So similarity-based methods actually find a similarity between nodes and use these similarity values to predict the link between those nodes. And embedding-based method, they actually embed the nodes into another space, like a numerical space, and then use the embeddings for link prediction. And factorization-based method actually used several matrix factorization to predict the link between nodes. And probability and statistics-based method, they actually use the probabilistic theory and some statistical theory to predict the links between nodes. So actually, I will focus on similarity-based and embedding-based approaches only. So similarity, as I told that similarity-based method are actually works on the assumption that two nodes in a graph interconnect if they are similar. So if the similarity scores are higher, means the probability of being connected of two nodes are higher. But the similar definition of similarity is a non-trivial and also a crucial task, because the performance of the similarity-based method depends on how one can efficiently design the similarity function. So common neighbor, this is one of the simple similarity-based method for link prediction. So in common neighbor method, two nodes are most likely to be connected if they have many immediate common neighbors. So in this figure, we are interested. Oh, I'm so sorry. We are interested to compute the link existence probability between nodes X and Y. So this is the neighbor, immediate neighbor of node X, and this is the neighbor set of node Y. And then a common neighbor computes the common neighbor from these two sets, and the size of the common neighbor set is the scoring function. So the common neighbor based similarity scoring function gives 3 for the link existence between nodes X and Y. And then common neighbors use this value for computing the probability between computing the link existence between two nodes X and Y. So again, similarity-based methods can be in 3 categories: local, quasi-local, and global. So local similarity-based methods, they actually use local neighborhood. The local neighborhood is defined as the neighborhood up to 3 hop neighbors. And quasi-local neighborhoods, they actually use the user-defined hop to define the neighborhood for computing the similarity-based function. And then global methods, they actually use global topological information to compute the probability of link existence between two nodes. So we are actually focusing only on local similarity-based metrics, because global similarity-based metrics are not suitable for large-scale graphs, because they actually use global topological information. So if a graph contains maybe 100,000 nodes, so it will be very much computationally inefficient to use global similarity-based matrices. And also quasi-local quasi-local approaches, they also takes mass computational time. So initially we have 13 local similarity-based methods. So based on their popularity, we use only 6 of them. So the popularity, we define the average citation per year to define the popularity of each method. So sorting out based on their popularity, I mean higher average citation per year, we actually select 6 methods among 13 local methods for the experiment in our study. So here is the list of these 6 used similarity-based link prediction methods. The first of all, academic adder methods. So it is actually very variant of common neighbor method. So it's actually logarithmically penalized is common neighbor by its degree. And then resource allocation method. Then, so here you can see the principle of each method. So if you are interested more into these methods, so you can get details in my paper. So compared to these 5 methods, the last method, CCLP, so this actually depends on clustering coefficient. So the clustering coefficient is defined as the triangle that is from centralized to a node. And so far, the similarity-based matrix, they actually work on the symbolic space. But in symbolic space, it is very difficult for the mathematical operations. So compared to symbolic space, numerical space enable us to do some mathematical operation. So embedding-based link prediction, they actually represent nodes in low-dimensional vector space. So it actually represents nodes in a way so that the similarity in the original network exist in the embedding space. And then it's train a classifier to classify the links into either existing links or non-existent links. So this is the input graph in symbolic space, and this is the embedding, the node embedding in embedding space. And for embedding-based link prediction approaches, there are actually 2 kinds of approaches. So first one of random walk-based approaches. So they actually samples the neighbors based on the random walk, and then use this node sequence to learn the embeddings. And for an graph neural network, so we know neural networks are very successful in computation vision domain. And graph neural network are just a variation of neural network that can work on graph. So in graph neural network, first of all, we need to define the neighborhood of a node and learn the node embeddings by aggregating its own embedding, its own information and neighborhood information. So for random walk-based approaches, we select node to peg. This is one of the popular node embedding approaches based on random walk. And for graph neural network-based method, we select 3 methods. First of all, WLNM. So later I will discuss more in details, but not very details, but maybe some intuition. So these approaches actually use only structural features of the graph, and these approaches use structural features and also node features. And graph attention network, this is another variation of graph neural network. I will discuss it later. So it is an improvement of graph conventional neural network. So this is not too big. So first of all, we have an input graph, and we generate the sequence of node by random walk, and we use the skip-gram model to learn the embeddings of the nodes. And then the node embeddings are used for generating a link embedding. So link embedding is generated by multiplying the node embedding, the embeddings of n nodes, and then use the traditional classifier like logistic regression-based classifier to with the embedding to classify it between existence and non-existent links. And Westphal-Lehmann neural machine-based graph neural network. So this is the architecture of WLNM neural network. So this is a 3 steps algorithm, where first of all, it extracts the neighbors of a link. So neighbors of a link is defined as the neighboring nodes of n nodes of the link. And then it uses the Westphaler-Lehman node labeling algorithm to label the nodes of the subgraph, and then uses the adjacency matrix of the subgraph for generating the link encoding, and then use the link encoding into a neural network to classify it between two classes. And now SEAL. So this is another popular graph neural network. So SEAL actually learn structure, latent, and explicit features for the link prediction task. So it is kind of a WLNM algorithm. So it is actually improvement of WLNM algorithm. So one point to mention, WLNM algorithm, this actually extract fixed size neighborhood set, like 10 or 20 nodes or 10 nodes like that. So maybe in some of the neighbors are filtered out in WLNM algorithm. So in SEAL algorithm, so they actually can take variable size neighbors. So in graph, a node may have a variable size neighbors. So SEAL can handle this variability. And it actually design a new node labeling algorithm that is faster than Westphaler-Lehman node labeling algorithm. So it actually, first of all, it extracts the neighborhoods, and then it labels the nodes in the subgraph, and then use these neighborhoods for generating that adjacency matrix like that, just like WNM algorithm. And then the node structural matrix that is quite similar to WLM algorithm. So then it also generate the latent feature matrix using node to bake algorithm. Then it also generate the explicit feature matrix using on-node coding. Then it concatenates all of these three matrices, and then use these matrices using a graph convolutional neural network to classify it into existent and non-existent link. So this one represent this is an existent link. I mean true link, and this is a false link. And graph attention network. So this is an improvement of popular GCN, graph convolutional neural network. So in graph GCN, all neighbors actually contributes equally during the convolution operation, but this may hamper the performance of GCN. So GAT actually introduce the attention mechanism to learn different weights to different nodes in the neighborhood. So it actually defines a graph attention layer to learn the weights. So this is an graph. This is an example of attention layer where HI and HJ are embeddings of n nodes, and W is a linear transformation matrix. And from these embeddings and linear transformation matrix, it actually learned a coefficient that represent the attention coefficient of the node of the link EI EJ. So then it actually works as like GCN. So it's just use this coefficient for aggregating the neighbors. And for comparing similarity-based and embedding-based methods, so the advantage of similarity-based methods is that it is actually easy to compute and fully interpretable, and no training required, and it consumes minimum computational time, and for embedding-based approach. So this is actually handcrafted methods. And for embedding-based methods, these actually learns this kind of similarity automatically from the graph. And there is no assumption on graph properties. And the drawbacks is similarity-based matrix actually handcrafted and has a strong assumption on link existence. The problem is embedding-based methods is the black box problem. We don't know what kind of heuristics they learn from the graphs. So in this study, we actually focus on open the black box problem. So for the experiment, we use 10 graphs from several domains. So the first 7 graphs are actually, we setting it as a small size graph because they have less number of nodes. And the last 3 graphs are higher graphs. So you can see that here is the domain of each graph. So for example, the E. coli graph, this is a representation of a E. coli bacteria network. And for NS, this is a co-authorship network for network from the network science publications. So you can see the description of each network here. And for the training and test data sets, we followed the 90%, 10% separation. So it means that 90% existence links are included in 10 dataset, and also an equal number of non-existence link is called negative links in the training dataset. And also in test dataset, we have 10% existence and equal non-existent links. And we build 5 training and 5 datasets by random sampling. And for the performance metrics, we use 2 metrics. The first of all, precision metrics. So for defining precision, we actually rank the test links in decreasing order of their similarity scores. And we pick top L rank links, and then we define the precision as LR by L, where LR is the number of existing link among the top L links. So we set top L links as the number of existing links in test links. And this method actually too much optimistic, especially because maybe some of the links in the top L links have scores, similarity score 0. We'll see it in the experimental result. To solve this optimisticity problem, we actually define a new method. So we actually define a threshold as the average of maximum and minimum scores among the similarity scores, and we redefine LR as the number of positive test link in top links that those have scores above the threshold values. And for computing AUC values, we actually iterate a process for n times. So for each step, we choose randomly on existing link and on non-existent link from the test set, and we actually increment n1 by 1 if the score of existing link is higher than the score of non-existent link, and increment n2 by 1 if the scores are equal, and use this formula for computing the AUC values. And for computing the precision AUC values for embedding-based approaches, we actually use the traditional classifier-based method for computing precision ANC. And we also recorded the computational time of each approaches. And here is the experimental result. So first of all, minimum and maximum similarity score. So here is the table. We can see that the methods actually show different similarity-based scores in terms of minimum scores differently. For instance, atomic adder, this similarity-based method shows 32.84 similarity, a maximum similarity score, and for power graphs, it actually shows only 3.04. So the maximum similarity values for all methods are different for different graphs, and also the minimum values are different in different graphs. And we see that in several graphs, the minimum scores is 0, but still in tuple links, we are considering them as actually truly positive links, because they have similarity score 0, but they are still in tuple links. That means the problem we raised here exists in the real world. So so computing the precision. So the first method, the first line, this is the precision computed by method 1. So, and this is the second line, this is the precision scores by method 2. And if we compare, the precision scores by method 2 is much lower than the precision scored by method 1 in all of the methods, in all of the graphs. And also the embedding-based approaches, they actually shows higher precision scores when comparing to method 2 scores. And we also see that the similarity-based methods actually shows higher scores in some graphs, but in some graphs it is much lower. Like these graphs, atomic adder shows only 0.07 precision, but in this graph it actually shows 0.9 precision scores. But for embedding-based method, they actually shows very good precision scores in all the methods. And also, if so, among the 10 graphs, power, router, and WN18, these 3 graphs are actually more sparse graphs. That means they have low average node degree. So in those graphs, similarity-based method actually show low values, low precision values. But in those graphs, similarity-based methods shows still higher link prediction values, link prediction precision values. And for AUC values, all of the methods show higher values. So in terms of AUC values, the similarity-based methods actually comparable to embedding-based methods. And among all of these methods, SEAL methods actually shows the highest AUC values in most of the graphs, because SEAL actually utilizes the maximum available information, like it utilizes the structural information and also node attributes information, and also latent feature information. And now we also compute the agreement between similarity-based and embedding-based method. So here you can see the percentage of agreement between top 2 ranked similarity-based method, which have a higher agreement with embedding-based method. So for this method, in this network, WNM has 69% agreement of link existence with ASPI and RA. And this actually opens the black box problem. So we can actually guess from this table what kind of heuristics actually the embedding-based method learns from a graph. So I'm so sorry, these texts are actually not right. And for in terms of computational time, obviously similarity-based methods are faster than embedding-based methods, because similarity-based methods do not need training. And for embedding-based method, node to bake requires the smallest time, because other three methods, they actually depends on neural network. So neural network actually takes much time to train the whole network, and it takes much time. So embedding method actually takes the smallest time. And the computational time of SEAL method is highest, because it actually computes the latent features and on-node coding of node features, and also utilizes the structural features. And overall, computational time of embedding-based method grows faster with the size of data sets, so it has less scalability. And major contribution of this study includes, we study several link prediction method, and we evaluate them on several graph data sets from various domains. And we present a method for computing precision of similarity-based method to overcome the difficulty of tuning threshold for deciding link existence. And we actually study to explore the possibility the possible links between the old-fashioned similarity-based method and the new embedding-based method by prediction performance comparison, and also link existing agreement. So it is actually, it supports actually it is an empirical study to support these possible links. And to conclude, we evaluate and compare two popular categories of link prediction methods, and we also introduce a method to overcome the difficulties in computing precision of similarity-based approaches. And our observation actually constituted a modest contribution to the black box limitation of embedding-based method. And future perspective could be developing an embedding-based method in a distributed and parallel environment to improve the computational time of embedding-based method, and also apply the method to heterogeneous graphs like knowledge graphs, because many of the real-world graphs are actually heterogeneous. And this is the references, and thank you so much for your attention.